Let us take some problems on shear force and bending moment. We are starting with question number 1. Let's take this example. For the beam loaded as shown in figure, here the diagram is given. Draw SFD and BMD. So first of all, whatever condition they have given, based on that we would be writing the data. Now in the data, first I would be drawing the beam which they have provided. Here there is 75 kilonewton of point load at a distance of 3 meter from right hand support. Next, at 6 meters distance from B, we have UDL up to the point load of 75 kilonewton. Intensity is 22 kilonewton per meter. Now this is the diagram which we have, and the question is draw SFD and BMD. We have to draw the shear force diagram and the bending moment diagram. So this much is the question part for us. Now we will start the solution for this. Here the first part is we have to calculate the support reactions. As we see, this is simply supported beam, so there would be reactions at end A, at end B. At A I'll call the reaction as RA, at B the reaction is RB. So first we need to calculate values of RA and RB. I'll say that step number 1 is calculation of support reactions. In support reaction calculation, here I have to say that at first the beam is in equilibrium, so I would be using the first condition, that is summation of Fy is equal to 0, where upward forces are positive and downward forces are negative. So therefore here I can say RA and RB, they are upward, so RA plus RB. 75 kilonewton is downward, so minus 75. 22 kilonewton per meter is the intensity of UDL acting at 3 meter distance. So if I convert it into point load, it would be 22 into 3, that gives me 66, and it would be in the downward direction, so minus 66 is equal to 0. Therefore RA plus RB will be equal to, if I add these values and I shift it onto the other side, I would be getting my answer as, that is 75 minus 66. If I add them, I would be getting this as 141. Keeping this as my first equation. Now after this I would be taking moments of all forces about point A. So I'll say that summation of moments about point A is equal to 0, where I will take clockwise moment positive and anti-clockwise moment negative. Therefore here I have RB which is acting upward. If I take the moment at point A, it would be anti-clockwise, so minus RB into 8. Then 75 kilonewton is acting downward, so it would be producing clockwise moment, plus 75 into 5. Next, this 22 into 3, it was 66 kilonewton acting at half, that is at 1.5. So from point A the distance would be 2 plus 1.5, that is 3.5. So here I have plus 66 into 3.5 is equal to 0. Therefore if I calculate the values here, that is this bracket 75 into 5 plus 66 into 3.5, shift it onto the other side, then divided by 8, I would be getting my answer of RB as 75.75 kilonewton. After getting RB, I will say that put RB is equal to 75.75 kilonewton in equation number 1. Therefore, here I have RA will be equal to 141 minus 75.75. So my RA value comes out to be 65.25 kilonewton. So these are my value of reactions, that is the support reactions. Now this completes my step number 1. In step number 2, I would be calculating the value of shear forces at all the points. So after this, I would be writing step number 2 as SF calculations, that is shear force calculations. So here first I will be starting with shear force at point A. So it is SF at point A, that is equal to, here my assumption is that the section is just at point A, or you can say just ahead of it, very close to A. This is my section, and as we can see, to the left of section there is RA, reaction at A, acting in the upward direction. The value is 65.25 kilonewton. RB was 75.75 kilonewton. So as per the sign convention, as I have told you all, that whenever you are calculating shear force, first mark the sign convention. Now the sign convention is, if we are taking a section, to the left of section if there is upward force, and to the right of section if there is downward force, both have to be considered positive. Next, if we have downward force to the left of section and upward force to the right of section, they have to be taken negative. So SF at point A, if I look here in the diagram, that reaction at A is in upward direction to the left of the section, so it has to be taken positive. Section, and to the left of section force is upward, so here I have plus 65.25 kilonewton. Next, I will be calculating shear force at point C, because between A to D the shear force will remain constant as there is no load between A to D. So after this I will say that SF at point C is equal to, if we look at point C, just before point C we have UDL and at point C we have point load. So it is better to calculate two values at single point C, one which would be to the left of C and other section would be to the right of C. So at a single point C we would be having two values of shear force. So first I'll calculate SF at point C to the left of section. I will say that this SF at point C will be equal to, if I am taking the left section, here I have RA to the left of section upward, so it is positive, 22 into 3, that is 66 in the downward direction. So if to the section, left to the section, we have downward force, that should be negative, so here I have minus 66. This gives me a value as minus 0.75 kilonewton. Next, again I will be calculating shear force at point C. and that will be equal to 65.25 minus 66, and we have to take even this 75 kilonewton because here I am taking the section to the right of C, so it is minus 75. Therefore my answer comes out to be minus 75.75 kilonewton at point C. After this I will calculate SF at point B. If I take the section just to the left of B, and if I see here, then to the right of this section I have RB which is upward, so it is 75.75 kilonewton, and if we have upward force to the right of section, that is negative, so here I have minus 75.75 kilonewton as the shear force at point B. Now as we have done SF calculations here, we are in a position to draw the shear force diagram. So after this I'll say that we are drawing the shear force diagram, and for that shear force diagram first we should draw the given beam which they have provided. This was the beam which they have given in the question. Now the first thing is, for drawing SFD, we need to project all the points downward, that is starting from point A, then point D, at last point B. Now for drawing shear force diagram, the length of the shear force diagram should be equal to the length of the beam. At point A, I am getting the value as 65.25. kilonewton. Then between A to D, we don't have any load, so shear force diagram should be a straight line. Next, at point C, we are having two values of shear force. One is 0.75 and the other value is minus 75.75 kilonewton. So these are the values which we have, and even we can say between C to B, since there is no load, shear force will be constant. As there is UDL between D to C, then shear force diagram should be an inclined line. Next, at point C, the shear force increases from 0.75 to 75.75 and then it remains constant, and finally it reaches the value up to 0. So here I have point A, D, C and B. I have written the respective shear forces. Upward forces, that is the forces which I have drawn above the line, they should be positive, and whichever are downward they should be negative. So this is the shear force diagram which we have. Now after this we would be calculating bending moment at all points. So here my step number 3 is BM calculations. That is bending moment calculations. As we can see in here that the beam is simply supported. So at the supports bending moment will be 0. I'll write down moment at A is equal to moment at B, and that is 0 into the bracket I'll mention since it is simply supported. Next I need to calculate moment at C. For calculating moment at C, first I will give you all the sign convention. Clockwise moment to the left and anti-clockwise moment to the right, they are taken positive. Anti-clockwise moment to the left and clockwise moment to the right, they are taken negative. So here if we see, when we are calculating moment at C, then to the right of C we just have RB, and this would be producing an anti-clockwise moment. So if I have a section and then to the right of section there is anti-clockwise moment, that has to be taken as positive. So here I have moment at C is equal to RB, which is 75.75 into 3. The distance is 3 meters from point C, from B to C, that is 3 meters. Now the value of moment at C, it comes out to be 227.25 kilonewton meter. Next, moment at D is equal to, here if I am calculating moment at D, to the left of D I have just RA, and this would be producing clockwise moment. So to the left of the section there is clockwise moment, so it is positive. So I have plus 65.25 multiplied by 2, and that value comes out to be 130.5 kilonewton meter. So these are the values which I am getting of moment at C and moment at D. Now with these values we can draw the bending moment diagram. So here we are drawing the bending moment diagram. As we can see in this shear force diagram, first of all, that there is one location where shear force is changing its sign. At that particular location shear force becomes 0. So I would be projecting this point down. Now we have calculated the values of bending moment at all critical points, but where shear force becomes 0, at that point bending moment will be maximum. Or in other words, you can say where shear force is changing its sign, at that location bending moments becomes maximum. So here I would be having one point where I would be getting the bending moment M as maximum. Next we have calculated moment at C, that is 227.25 kilonewton meter. Moment at D is 130.5 kilonewton meter, and moment at A and B, they are 0. So here we would be drawing bending moment diagram after marking the values, as we see between A to D, shear force is constant. So whenever shear force is constant, bending moment should be an inclined line. Next, between D to C, shear force is an inclined line. So bending moment, it should be a curve, that is a parabola. It is a parabola. Between C to B, it is a straight line. So bending moment should be an inclined line. Here I can say that we are having parabola from D to C. And since all the values of bending moment, they are positive, I'll mark plus sign here. So this is the bending moment diagram which we have. Now after getting this bending moment diagram, this problem is not completed yet. Here we need to calculate the value of maximum bending moment, because we have calculated bending moment at A, B, C and D, out of which we can see at point C the bending moment is 227.25 kilonewton meter, but we are having a value which is more than 227, and that is the maximum bending moment. That value we have to calculate. So how to get that value? I would be writing here calculation of maximum bending moment. To calculate maximum bending moment, first we should know the distance of this point where maximum bending moment is acting. This distance we will find it out from point D. I'll call it as X. If we are in a position to get this value of X, we can easily calculate bending moment at this point. So I'll say that from the similarity of triangles, here I would be magnifying these triangles. That is, here I have a bigger triangle whose base is X, and here I have a smaller triangle. So these two triangles I would be drawing here. This distance is X. Between D to C it is 3 meters. So from C to the location of this point, that becomes 3 minus X. So here I have distance as 3 minus X. So from these two triangles, I would be writing that the height of the bigger triangle, that is 65.25, the height of the bigger triangle divided by the base of the bigger triangle, which is X, will be equal to the height of the smaller triangle, that is 0.75, divided by the base of the smaller triangle, that is 3 minus X. So therefore 65.25 into 3 minus X is equal to 0.75 X. Therefore 65.25 into 3 minus 65.25 X is equal to 0.75 X. So therefore if I calculate the values here, that is, if I shift 65.25 X onto the other side, it would be added to 0.75 X, and that becomes 66 X. Then if I calculate 65.25 into 3, the value is 196.75, and hence X will be equal to 196.75 divided by 66. The answer is, it is 2.96 meter from point D. So I have calculated the location from point D where shear force becomes 0, and this answer of X is 2.96 meter. Now I will be calculating the bending moment at this point. So I'll say that taking moments at a point which is 2.96 meter from point D. So here I'll take the moments at this location where SF is changing its sign. So if I calculate the moment here, it would be, first my section is here, I would be transferring this point to the diagram of the beam. Here is my section, and if I see to the left of section, RA will be producing clockwise moment, so that has to be taken positive. So plus 65.25, and the distance is 2 plus 2.96. So it is maximum bending moment into 4.96, because this distance is 2 plus 2.96, that is 4.96. Next, this 22 kilonewton per meter will be acting at 2.96 distance. So it is minus 22 into 2.96 acting at half of 2.96. So here if I calculate all the terms, I will be getting my answer of maximum bending moment as 227.26. It is fractionally greater than moment at point C. That is, at point C I was getting the bending moment as 227.25 kilonewton meter, and my maximum bending moment is 227.26 kilonewton meter. So just a fractional increase, and we have given in this problem, it was asked to draw the SFD and BMD, and here we have solved the question and completed the shear force diagram and bending moment diagram. With this, the problem is completed.